All right, your homework questions from page 270 with efficiency. Number 44, remember our equation for efficiency is either work out over work in times 100 or energy out over energy in times 100. Okay, so depending on what you're given. So in number 44, a portable stereo requires 265 joules of energy to operate a CD player, yielding 200 joules of sound energy. So it's giving us what it needs, it requires, so that's what has to go in, and what it's putting out to get yielding 200 joules of sound energy is our out. So 200 joules over 265 joules times 100. And our percent efficiency is going to be 75.47%. And I lost the EFF there, sorry about that. Okay, part B, where does it go? And it goes to heat. If you've ever taken a CD out of the CD player after it's shut off, it's hot. Number 45 is a little trickier. 45 has a kid up here on the slide who's now going to slide down here. Now to get up here, the kid has to do some amount of work, and it says they're sitting 1.8 meters above the ground. So the work in, or the energy in, is just like F delta D, right, cos theta, but it's going up, and so the cos theta is just going to be 0. The F to get the kid up there is just going to be mg, and the delta D is really just the change in height. So the energy going in is equal to mg delta H. The energy, which is the work you've done to get him up there, the energy coming out, the kid's going to have a speed at the bottom. And so the out is just going to be the kinetic energy, 1/2 mv and final squared. So when we do our efficiency of out over in, it's going to be 1/2 mv squared on the top and the mg h on the bottom. So 1/2, the mass of the child is 49 kilograms. And the speed at the bottom is 3 meters per second. And don't forget to square it. And then 49 kilograms times 9.81 meters per second squared. And the height was 1.8 meters. Oh yeah, and then times 100 to find the efficiency. And when you do this, I think you get a very sad 25.484%. Not very efficient. Clearly, whatever pants the kid has on, it's not doing a lot on the slide. It must be a lot of friction because they're losing 3/4 of their energy on the way down to probably friction. Okay, number 46. A machine requires 580 joules of work, of energy. If it requires it, it means you need to put it in 580 joules of work to do 110 joules of useful work. So that'll be what's coming out. And that, again, it could be I or W or E. If you're not clear, remember the bigger one always has to be what goes in. So percent efficiency will equal out over in times 100. So 110 on the top, 580 on the bottom, times 100. And you get a percent efficiency of 18.9655%. So again, nothing very exciting. Remember I had said if you get anything over 70, you're usually really happy. These aren't even close, so it's not, that machine, just like the slide, is not very efficient. Number 47. Incandescent light bulbs transform 120 joules of energy to produce 5 joules. So for the incandescent ones, percent efficiency, again, out over in, times 100. So you get 5 joules out and it needs 120 joules going in. Clearly not efficient. So for the incandescent bulbs, you get an efficiency of 4.16 with the 6 repeating percent. For the fluorescent, percent efficiency again, out over in. So this time it says it only requires 60 joules of electrical energy to produce the same amount of light. So the light you're getting is your out, and this time it's 60 joules on the bottom. That's all you have to put in. And so the percent efficiency for the fluorescent is going to be 8.3 repeating. So it's twice as efficient percent, okay? But still really pretty lousy, even though it's twice as good. Okay, and then it says why are the fluorescent more efficient? They're more efficient because they give off less heat than the incandescent. All right, number 48. Percent efficiency equals out over in times 100. And so it says it transforms 345 joules of radiant energy into 301 joules of thermal. So 301 thermal is the heat you're using to cook your food. The 345 is what we're putting in times 100. This is going to be a much better efficiency, 87.246%. So the microwave finally is giving us something good. Number 49 says a 125-gram ball is thrown with a force of 85 newtons and acts through a distance of 78 centimeters. So that's your work in. Remember, work is equal to F delta D. So you're applying a force of 85 newtons. And you're applying it over, sorry, there's also a cos theta there, but it's 0. And you're applying it over a distance of 78 centimeters, or 0.78 of a meter. So you can find the work that you're actually doing on the ball, and when you do, it's 66.3 joules. Then it says the ball's velocity just before it's caught is 9.84 meters per second. So that's going to be what your energy out. And remember, it's okay to, will be the same as your workout. Okay, so it's kinetic energy, 1/2 mv squared. So 1/2, the mass was 125 grams, or 0.125 kilograms. And the speed out was 9.84 meters per second. And don't forget to square it. And when you do, you get 6.0516 joules. So now you have your out and your in. Actually, put the paper up here. So your percent efficiency, we'll use W this time, W out over W in times 100. And so 6.0516 joules over 66.3 joules times 100. And you're going to get an efficiency of 9.1276%. Okay? So it says, so part A, calculate the work done. Part B, calculate the kinetic energy. And then it says, what fraction of energy transferred to the ball was lost? So this is how much it still has. So what would be lost would be the 100% minus this. 1276. So what's going to be lost is 90.8724%. Okay? Not really great. And the last one, number 50, says rubbing your hand together requires 450 joules and you get out 153. So again, percent out over in, gonna run out of time. So on the bottom, on the top 153, on the bottom 450 times 100, and you should get 34%. Okay? Next video, the kinetic energy questions.